All right, this is another big one. Last lesson, we didn't really do anything with Taylor series. I just showed you what a Taylor series was. So a Taylor series is a type of power series that converges to an actual function. So last class, I derived basically the Taylor series for e to the x. And if you remember, I showed that e to the x is simply just 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus dot 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 plus x to the n over n factorial. And this can be represented by the sigma notation for x to the n over n factorial starting at 0 to infinity. So you have the function that it converges to. You have the infinite series expanded out, the first four terms and the general term, and then you have the sigma notation that sums it all up. It's a pun because it's a sum. Anyway, I went through a very lengthy process on doing this, meaning I had to find the first derivative, and then I used that thing where I solved for a and b and c and d, and then I've come up with I recognize the pattern. You're not going to do that. There are essentially three ways we build Taylor series, and the way I did it last class, you're never going to have to do. So the question is, how do you build a Taylor series? Well, the way we are going to focus on today, and then we're going to practice a bunch, is you use the formula. So, long story short, there's a nice formula that we were actually using last class, or last lesson, but it was kind of hidden in the work I was doing. But here is the formula for building a Taylor series. Taylor series formula works like this. It says that f of x equals f of c plus f prime of c times x minus c, I'm just reading something, plus the second derivative at c over 2 factorial times x minus c squared plus the third derivative at c over 3 factorial times x minus c cubed. And that just continues on and on and on. And in general, it's f to the, and then we're going to use a little n for nth derivative at c over n factorial times x minus c to the n. Just for that. That's your very, 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 very important formula for constructing any Taylor polynomial. So you need to have this thing down. And we are going to practice using it a bunch. Let's talk about a few things. What on earth is C? C is called the center. What is the center? It's where your Taylor series is most accurate. So last class, we centered our Taylor series around 0. X equals 0 is the center. That's the logical center for a lot of these, as we'll see soon enough. But you can technically center it wherever you want. So with that, let's build our first Taylor series using the formula. And let's build it for sine. So here's an example. We're going to find the Taylor series for f of x equals sine x. But I'm going to be annoying about it. Centered at x equals pi over 6. If it was 0, this problem would be a lot easier, which we'll get to that one. But I'm going to give us a challenging one to start. All right, so let's do the work. Well, we're going to need a bunch of these f of values. So we may as well start by finding f of the center. F of the center is sine of, plug in the center to sine of pi over 6. Hooray, we get 1/2. Hooray for trig. All right, let's take a derivative. F prime of x is, derivative of sine x is cosine x. So f prime of pi over 6 is equal to the cosine of pi over 6, which is rad 3 over 2. Hooray. Let's find the second derivative. Second derivative of cosine of x, or second derivative of sine x, which is the derivative of cosine x, is negative sine x. Plug in the second derivative, plug in pi over 6. We get negative sine of pi over 6, which is negative 1/2. And then let's find the third derivative of the x, which is negative cosine x. And then we plug in pi over 6 to that. And we get negative cosine of pi over 6, which is negative rad 3 over 2. Cool. So we have these terms that we are going to use when we come up with when we use the formula. So let's plug into the formula. Formula says the first term, f of c. Well, we already found that because we're centered at pi over 6, so that would be 1/2. Plus the second, or the first derivative of the center, which is rad 3 over 2, times x minus the center, which is pi over 6. Plus our next term, which is the second derivative, which is negative 1/2. So now we're at a negative value. So I'm going to make this a minus 1/2 over 2 factorial, because now we're doing this term, times x minus pi over 6 to the squared power. And then it looks like it's going to be one more minus. Oh, we just did that one. The next one, minus rad 3 over 2 over 3 factorial x minus pi over 6 cubed plus dot, dot, dot. And this is infinite series, so it goes on and on and on forever. And one of the things, this is called the Taylor series. It's an infinite series. If we cut it off at the third term and we just gave the first 4 terms the third degree, that'd be a third degree Taylor polynomial. But what I want to do is see how good this did. So bear with me. Remember, we are coming up with a Taylor series for sine x, centered at pi over 6. Pi over 6, are we in radians? I want radians. Wait, it is in radians, but let's start this. Watch, ready? Negative pi to pi. 1 pi over 6. There we go. Cool. I just wanted to do that so that it actually looks like a sine curve with radians. Okay, so remember, we're centering it at pi over 6. Pi over 6 is right there. So this thing I'm about to graph should be super accurate in this area and then get worse as we go off, because I'm only going to do third degree. So how do I get this out of the way? Let's do this. All right, here we go. So 0.5 or 1/2 of x equals 0.5 plus square root of 3 over 2 x minus pi over 6. No. Yeah. Look, there's your tangent line approximation at pi over 6. Not bad. Obviously, it's a tangent line. But we went one step further, and we have 1/2 divided by 2 factorial. I want to make sure that's going to give me the right way to do it. Hold on. Let's do this. When you divide by 2 factorial, it's like multiplying by 1 over 2 factorial. So technically that 2 factorial is in here. I'm just going to put it here so that we don't accidentally mess something up. And then times x minus pi over 6 squared. Looks pretty good. It kind of bends, but obviously it's a quadratic, so it doesn't bend back the other way. So let's add the next level, which is minus square root of 3 over 2, all over 3 factorial. But again, just like in the last problem, technically that's the same as putting 3 factorial in the denominator of the original fraction. And then x minus pi over 6 to the third. And check that out. That looks even better. So right at pi over 6 is perfect. Near pi over 6 is pretty darn good. It gets worse as we go. And we could just keep adding terms. The next term, it's going to repeat itself because now we're back to sine again. So we could do one more term. We don't actually have to 1/2 times 4 factorial times x minus pi over 6 to the 4th. Even better. So as you add more terms, your Taylor polynomial approximation gets better. This one's centered at pi over 6. So here's the thing. It's kind of hard to recognize any patterns. So if you were to try to come up with a general term, I'm not even going to do it here. Like in the last one, we came up with this thing called the general term in the original. Look, it was very nice. We saw a pattern. In this, it's hard to see a pattern when we're not centered at 0. So I am going to give you the Taylor series centered at 0 for sine. It looks like this. So here is your, by the way, well, we'll get to that in a second. This is the Taylor series centered at the center being 0 for sine of x. It looks like this. Ready? Sine of x equals, the first term is 1. Then it goes minus x cubed. Well, wait. That's not 1. I almost messed that up. It is x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial plus dot, dot, dot. So if I come back to this and I redo, come on, and I get rid of this and I do it again, and I say f of x equals, I did this in the last video, so x minus x to the 3rd over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial plus dot, dot, dot. I'm actually going to do that, but it goes on and on and on. And then look, that's centered at 0. So this is going to be an important one that comes up a lot. Can you find the general term? Well, the general term, we got to see what's going on with the powers. The general term would look something like this, and this is going to be the hardest part of Taylor series when we start to do this part. Can you come up with a general term? I'm just going to give it to you for this one. It is negative 1 to the n, because this is alternating. See? Negative, positive, negative, positive. X to the 2n minus plus 1. We'll talk about that later. All over 2n plus 1 factorial, because these are odd powers. So what does the sigma notation for that look like? It looks like the general term, so negative 1 to the n, x to the 2n plus 1 over 2n plus 1 factorial. Starting this series at 0, so when you plug in 0, you better get x for the first term, and you do. Better get positive x, and then it goes to infinity. And that is your Taylor series centered at 0 for sine x. Now, it's going to get really annoying to say Taylor series centered at 0. So I shouldn't cross that out, actually. Let's fix that. We're going to use a different language instead. A Taylor series centered at 0 is called a MacLaurin series. Sorry, MacLaurin is just a Taylor series when the center is 0. So that's why this lesson is called the 4 big MacLaurins. We've now seen 2 of them. We've seen the e to the x MacLaurin, and we have seen the sine of x MacLaurin. That's 2 of the 4. There are 2 more. So sine of x is a big one. What's the next big one? Cosine of x. So let's do this one. I'm not going to give you this one. I'm actually going to have us build it. Let's build the Taylor, MacLaurin, which means it's centered at 0, for f of x equals cosine of x. All right, so we're going to go back to our formula, which means we need to find f of 0, f prime of 0, f double prime of 0, f triple prime of 0, and hopefully by then we can establish a pattern. I actually bet we're going to need more, because you're going to see something interesting happen. So first derivative, plug in 0 to cosine, plug cosine in 0 is 1. Then f prime of 0 would be the sine, because the derivative of cosine is actual negative sine. So think it's negative sine of 0, and that is 0. Does that happen? Oh yeah. and we'll talk about why that happens in a second. The derivative of negative sine is negative cosine of 0, which is -1. Derivative of negative cosine is sine. Sine of 0 is, another 0. Derivative of sine is cosine, and we're kind of back to our repeating spot again, which is 1. So look at these terms as we start to build the series for cosine of x. The first term is 1 plus 0, don't forget 0, times x minus the center, which is 0. Plus, but it's a minus, so minus 1 times x minus the center squared over 2 factorial. I'm hoping you're seeing this. The next term is going to be 0, x minus 0 cubed over 3 factorial. The next term, we are back to a 1, is plus 1 times x minus 0 to the 4th over 4 factorial. Now, what are all these zeros causing to happen? Well, that term's gone and that term's gone because you're multiplying by 0. So what is cosine of x looking like? 1 minus x squared over 2 factorial plus x to the 4th, we skipped over the 3rd, over 4 factorial. Notice we're skipping the odd-powered ones because those odd-powered ones are getting coefficients 0, just like for sine. That's why sine didn't have the even-powered ones, same kind of logic. So what about the general term for this one? It too alternates, but instead of x being to an odd power, x is going to be to an even power, just like this. And that would also be the sigma notation. I won't write it again. So there's a third big MacLaurin, the cosine of x one. Okay, there is one more, which we'll get to. But before we get to it, I want to show you something pretty sweet now. So the reason we are going to be dealing with Taylor series is it is a different language of dealing with our common functions that allow us to do a lot of interesting things. When you can turn a function like cosine into a polynomial in an infinite series like this, you can do a lot of things as a polynomial that you couldn't do with this closed form of cosine. But that's for another day. Instead, I want to show you some neat things about the language of our new Taylor series. So, some interesting things. We just derived cosine of x by using the formula, which is great. The formula is a great way to do it. But there are other ways that you can find a MacLaurin or Taylor series. Let's go back to the sine of x infinite series, which was x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial plus ... First 4 terms. Okay, so what I'm trying to tell you is this thing on the left equals this thing on the right. Sine of x can be represented by this infinite series. This infinite series converges to sine of x. That means anything I do to the left and do to the right will maintain equality. So any operation we do on sine, if I do it on this series, is totally valid. So that includes things like, what if I take the derivative of both sides? Well, what is the derivative of sine? It's cosine. What is the derivative of each of these term by term? Derivative of x, 1. Derivative of this term is just a power rule. So put the x in front, decrease the power by 1. Plus, same rule, power series, or it's a power rule. Put the 5 in front, decrease the power over 5 factorial. Minus, what happens? Put the power in front, decrease the power. Cool. Okay, well, can we simplify this a little bit? Yeah, 3 over 3 factorial. Remember, 3 factorial, actually, let me get rid of that. 3 factorial is just the same as 3 times 2 times 1. So I can cancel that and that 3, and I'm left with x squared over 2 factorial, because 2 times 1, which is 2, plus, can I do the same thing here? Absolutely. 5 times 4 times 3 times 2 times 1. Cancel the 5s. X to the 4 over 4 factorial. Minus, cancel the 7 from the 7. You get x to the 6 over 6 factorial. Plus, dot, dot, dot. So look, I just found the MacLaurin for cosine of x. But wait, didn't we already do that? Does our answer match the answer we just found a second ago? It does. So it's not just a coincidence. This new language, everything works that worked in our old language. This really does represent cosine of x. This infinite series is exactly equal to cosine of x. It converges to cosine of x. This Taylor series converges to this function. So what about our other series? We just talked about e to the x at the beginning. E to the x was this, x plus x squared over 2 factorial plus x cubed over 3 factorial plus x to the 4th over 4 factorial plus. Well, same logic. What if I reduce this or take the derivative of both sides of this? The derivative of e to the x is e to the x. That's weird. Well, what's the derivative? I take the derivative, or what is the derivative of this series? Derivative of 1 is 0. Derivative of x is 1 plus derivative of x squared over 2 factorial. That's a power rule. So 2x over 2 factorial plus derivative of x cubed is 3x squared over 3 factorial plus derivative of x to the 4th is 4x cubed over 4 factorial. And just like I did in the previous one for sine, we can cancel the 2's. We're left with x. We can cancel the 3 and the 3 factorial, and we're left with x squared over 2 factorial. 1. Do the same thing here. Cancel the 4 with the 4. We're left with x cubed over 3 factorial. And what do you notice? Oh my gosh. That is literally the series for e to the x. So again, our language works here too, which is pretty impressive if you really think about it. The same rules for the derivative of e to the x work for the infinite polynomial presentation of e to the x. So I think that's super cool. One last topic here. We're going to find the MacLaurin for this obscure function, which I kind of brought this up the other day in class. I'm curious if you actually remember it. Why? Why this function? Well, this serves a purpose when we're dealing with something that we'll get to in a second. But we're going to use it building our centered at 0, so it's MacLaurin. So f of 0 is equal to 1. F prime of x is equal to, well, we're probably going to have to rewrite it as 1 minus x to the negative first. It's a chain rule. So negative 1, 1 minus x to the negative 2, but then times the derivative of the inside, which is negative. So now let's plug in 0. So f prime of 0 is the negatives cancel. 1 minus 0 is 1. 1 to the negative 2 is still 1. All right, let's find so we simplified this as just 1 minus x to the negative 2. All right, let's find the second derivative. And second derivative is going to be negative 2 times 1 minus x to the negative third times negative 1, which again, the negatives are going to keep canceling, by the way, and we're left with 2 times 1 minus x to the negative 3. So when we plug 0 into that, we get 2. Okay, let's find the third derivative and maybe hopefully find a pattern. Third derivative of x is equal to, it's another chain rule, negative 6 times 1 minus x to the negative 4 times negative 1, which is 6 times 1 minus x to the negative 4. Plug in 0. The third derivative at 0 is 6. Let's do one more. By the way, this 1, 1, 2, 6 combination should become pretty obvious to you as we do this more and more. But let's see if you can get the next number. The fourth derivative, negative 24, times 1 minus x to the negative 5th times negative 1. And I think we've seen this enough now. The negatives cancel. You plug 0 and you get 1 inside, which equals 24. Do you recognize these? the 1, 1, 2, 6, 24, those are your factorials. So this is 0 factorial, 1 factorial, 2 factorial, 3 factorial, 4 factorial. All right, let's build the MacLaurin. So the first term is 1. So 1 over 1 minus x is equal to 1 plus 1 times x, so x, plus 2 factorial, so 2 factorial times x minus 0 squared over 2 factorial, plus 3 factorial times x cubed over 3 factorial, plus 4 factorial times x to the 4th over 4 factorial. And hopefully you're catching on to what's happening. These just keep canceling. So we've discovered our MacLaurin for this weird series, which is 1 plus x squared plus x cubed plus x to the 4th plus ... In general, x to the n. But we could have saved a ton of time without having to do this, and this will be a future lesson, and this is why this series is so important. Look at this series I just created to go from one term to the next. What are you doing? I'm multiplying by x. 1 times x is x. X times x is x squared. X squared times x is x cubed. That means this is geometric. And if it's geometric, that means it has a first term. That means it has a ratio. And can you find the sum, aka what the series converges to with these two pieces of information and the fact that it's geometric? Yes, it is the first term over 1 minus the ratio, which is exactly what this function was. So that's why this one's important. It's our sum formula for geometrics. But now we have a new way of thinking about it too. We can represent it. This is a Taylor series that converges to this function, and this Taylor series is geometric, so we also can treat it like the sum of this. It's kind of an overlap between a Taylor series and a geometric. So this is just a little bit to show you some things about our new super fun Taylor series and our big 4 MacLaurin series and how we're going to start using them. I don't want to go much further. I'm at 27 minutes, which is a lot, but this one's really cool for getting approximations for a lot of interesting things. So we will come back to this, but I will leave us there for now. All right, that's it.